Let us look at a few more aspects of the second law of motion. So firstly, we'll begin by looking at an object whose velocity is approaching the velocity of light. Now, the mass of an object, m, is given by mo square root of 1 minus v square by c square, where m0 is the rest mass, that is the mass when the object is at rest. V is the velocity of the object. C is the velocity of light, 3 into 10 raised to 8 meters per second. So the mass of an object depends upon its velocity, and it is given by this particular equation. M is equal to m0 square root of 1 minus v square upon c square. So we can find out the mass of an object at a particular velocity. So let us say an object of mass mo is 50 kg, let us say, and its velocity is 0, then let us say becomes 10 raised to the power 2 meters per second, 10 raised to 4 meters per second, after that 10 raised to 6 meters per second, and then 10 raised to 8 meters per second. Let's find out what is the mass of an object of this particular mass whose rest mass is 50 kg at, let us say, 10 raised to 4 meters per second. So if I put the values in this particular equation, m is equal to 50 divided by 1 minus velocity is 10 raised to 4, so 10 raised to 4 squared divided by 3 into 10 raised to 8 whole squared, and with this the mass of the object will be come out to be around 50.0003 kg. So you can see that the mass has increased, but the increase in mass is negligible. Let us see what happens when the mass of the object becomes 10 raised to 8. So in that case, if I do the same calculation, 50 square root of 1 minus 10 raised to 8 whole squared divided by 3 into 10 raised to 8 whole squared, I'll get a value of around 53 point something, 53.02, let us say. I'm not very sure about these two numbers, but it will be 53 point something kilogram. So we can see there is a substantial increase in the mass. It has increased by 3 kilogram. And this is what is observed, that when the mass of the object is, rather the velocity of the object is below 10 raised to 6 kilogram, 10 raised to 6 meters per second, the increase in mass is negligible, whereas beyond 10 raised to 6 meters per second, the increase in mass is not negligible, it is substantial. So if I am going to use the equation F is equal to ma, the second law of motion for this object, I can use it only below velocities of 10 raised to 6 meters per second, because below 10 raised to 6 the mass remains constant, and we know that in this mass is a constant. Beyond 10 raised to 6 the mass is not constant, it keeps on changing as the velocity keeps on increasing, and therefore we should bear this in mind, that you can use this equation, second law, only when the velocity of the object is approximately less than 10 raised to 6. Please keep in mind this 10 raised to 6 is not a very sharp, clear cut drawn boundary line. We are just saying that around that particular value or less than that the mass remains nearly constant, and beyond that the mass increase is substantial enough for us not to ignore it. So second law of motion can be used only for velocities less than approximately 10 raised to 6 meters per second. The second aspect of Newton's second law of motion that we will look at is the first law of motion, and how we can derive the first law of motion from the second law. So according to the first law, when no unbalanced force acts on an object, it continues to move with uniform velocity. It continues its uniform motion. This is what the first law says. Now if I use this in the second law of motion, the second law of motion says that F is equal to ma. So when there is no unbalanced force, that means F net or F is equal to 0. Now F is ma, that would mean ma is equal to 0, because when there is no unbalanced force, F net is 0 and F is m into a. So ma is 0. If ma is 0, either m has to be 0 or a has to be 0. M cannot be 0 because that is the mass of the object. Therefore, from this we will say that a is equal to 0. That means the acceleration of the object is 0. Therefore, v minus u over t is 0, and therefore v minus u equal to 0, and finally we will get v is equal to u. That means the initial and final velocity are same. That means this implies that the object is moving with uniform velocity. Thus, when there is no unbalanced force acting on the object moves with uniform velocity. In the third part of this video, let us look at some real life examples of second law of motion. Before we look at the real life example, let us look at it from a math perspective. We know that F force is given by delta P by delta T, change in momentum per unit time. Let us fix up the value of delta P. Let us say the value of delta P is 50 kg meter per second. So, if delta P is constant, then what will happen is force is inversely proportional to T. Therefore, as time keeps on decreasing, the force will continue to increase. Let us take some values. Delta P is 50. So, if I take T is equal to, let us say, 0.1 second, in that case force will be delta P by T, which is 50 divided by 0.1. Delta P 50 times 0.1. This will give me a value of F as 500 Newton. If I take T as, let us say, 1 second, F will be delta P by T 50 divided by 1, and that will give me a value of F as 50 Newton. Third, let's take one more value. T is equal to, let us say, 5 seconds. That means this change in momentum is occurring over a period of 5 seconds. In this case, it was occurring over a period of 1 second. So the change in momentum is occurring slowly because it is taking 5 seconds for that change to happen. So F will again be delta P by delta T 50 over 5, and that will give me a value of F as 10 Newton. So we can very clearly see that as time is increasing, the force is decreasing. What is this time? This time is the time required for this change in momentum to occur. If the change in momentum occurs slowly, as seen over here, taking 5 seconds, the force applied is small. But if it occurs very quickly, force applied is larger. Based on this understanding, let us look at a couple of real life examples. Let us say we have a car of mass 1000 kg which is moving at a speed of 25 meters per second. Let us say it is out of control. Now it has two options. Let us say it can crash into a concrete wall or it can crash into a haystack. Obviously, the driver will prefer to crash into the haystack. This he will do spontaneously. What is the physics behind it? Yes, it is the second law of motion. So let us analyze these two cases. In both the cases, whether he crashes into a concrete wall or the haystack, change in momentum is same. Delta P will be equal to mass into change in velocity. Mass is 1000 kg of the car. Final velocity is 0 because after crashing the car has to come to a standstill, so V is 0. Initial velocity is 25. So this will give me a change in momentum of 25,000 kg meter per second. For the moment I will ignore the sign. The negative sign is coming because the velocity is decreasing. So the change in momentum is 25,000 kg meters per second. Now when the car crashes into the wall, this change in momentum occurs very quickly. The moment it hits the wall, it comes to a stop. So let us say the time that it requires, or the time that is used up for this change in momentum is very small. Let us say it is 1 second. So if that is the case, what is the force that gets applied on the car? Force we know is delta P by delta T. Delta P is 25,000 divided by 0.1. This will give me a value of the force acting on the car as 250,000 Newton. You can imagine this force. The moment it hits the wall, a force of 250,000 Newton acts on it, and therefore it leaves a major impact on the car, as shown over here. When it crashes into the haystack, the time required for the velocity to become zero is more. So let us say it happens over a period of, let us say, 2 seconds. So in that case, what will be the force that will be applied on the car? Delta P by T, again the same calculations. 25,000 is the change in momentum divided by 2. This will give me a value of force as half of 25,000. That means 12,500 Newton. So a much smaller force gets applied, and therefore the impact on the car is very small, negligible as compared to the previous case. Look at this. This is 12,500. This is 250,000. This is 12,500. So this is one more application of the second law of motion. Let's look at one more example, that of a karate expert who is using his hands to break a brick stack. So number of bricks are placed, and the karate expert, what he does is he moves his arms and hand swiftly and hits the stack of bricks. So let us understand this very closely. He moves his arms and hand very quickly. Therefore, his arms and hands have a very large velocity before they hit the bricks. So if this is the brick stack, let us say these are the brick stack. When the hand is about to hit the bricks, its velocity is very high. The moment it hits the bricks, the velocity of the hand becomes zero. So it becomes zero in a very short time. F we know is equal to delta P by T. The change in momentum is fixed. This particular will have some particular value. This T is extremely small, and therefore F is very large. And therefore he is able to break the brick stack. So he does it by making sure that the change in momentum occurs within a very short time. So these are some of the examples of application of second law of motion. There are more examples. For one of the most common example is a glass falling on a carpet. So let us say we have a small glass and it falls on a carpet. The chances of it breaking are very small, because when it falls on the carpet, the change in momentum occurs over a large period of time, and therefore a smaller force gets applied. But if the same glass were to fall on a hard wooden floor, the moment it hits the wooden floor, the velocity would become zero within a very short time. Therefore a large force would get applied on the glass and it would break. Right, with this we have completed our discussion on Newton's second law of motion. In the next video we will study the third law of motion and see how it is connected to the second law and the first law.